Hello, so today we're going to be looking at electron configurations. By the end of this session, you will hopefully be able to complete electron configurations for elements up to Kr, write electron configurations in an abbreviated form, and identify the S, P, D and F blocks within the periodic table. So, to start with, I want you to have a think about this. What were the GCSE, or what are the GCSE rules for electron configurations? Have a think about that now. Okay, so if you remembered, so the GCSE rules that you were taught is there were 2 electrons in the first shell, 8 electrons in the second shell, possibly 8 electrons in the third shell. You may have been told that there were 18 electrons in the third shell. You may have just been told there were 8. You only ever had to go up to 20 electrons in total, which would be 2, 8, 8, 2. Okay? So using the periodic table, using the electron configurations for GCSE, have a go at writing out the electron configurations for sodium and for carbon. Okay, so sodium is here. And you can see it's got 11 electrons because the atomic number is 11. The atomic number is the one at the bottom. So that means there would be 2 electrons in the first shell, 8 electrons in the second shell, and then 1 electron in the third shell. So that's sodium. Carbon is over here. It's got 6 electrons. So carbon has got 2 electrons in the first shell and 4 electrons in the second shell. You may also notice and remember that the group number corresponds to the number of electrons in the outer shell. So in this example, sodium has got 1 electron in the outer shell and it appears in group 1 of the periodic table. And carbon has got 4 electrons in its outer shell and it therefore appears in group 4. So what's changed at A level? Well, electrons are arranged in shells. We still will refer to them as shells, but you may hear them referred to as energy levels. And there are still 2 electrons in the first shell, and there are indeed 8 electrons in the second. However, we also need to think about subshells. So subshells are how the electrons are arranged, but they're also arranged in the main shells as we would have looked at GCSE. So this is what's important. So the S subshell, holds 2 electrons in total. It's got 1 orbital. So an orbital is a place where electrons will go. An orbital can hold 2 electrons in total. The S orbital looks like a circle, okay, or it's a sphere. You may be asked to draw out the S orbital if you do the EDEXCEL exam board. However, if you do the other exam boards, you won't be expected to draw out the orbitals. Okay, but an S orbital essentially is able to hold 2 electrons, so it's a pair of electrons. Orbitals will fill up with 2 electrons. They will go, 1 is what we have up spin, so it's usually represented with an arrow pointing up. And the second electron will have down spin, so it's represented with an arrow pointing down. The P subshell holds 6 electrons. There are 3 orbitals in the P subshell. There's Px, Py and Pz. A P orbital looks a bit like an elongated figure of 8. Okay, so there are 3 P orbitals. Okay, electrons will fill the P orbitals separately at first, so the 3 electrons will fill like this, and then they will start to pair up like this. Okay, so in total the P subshell can hold 6 electrons because there are 3 orbitals. A D subshell holds 10 electrons. How many orbitals is that? That's right, that's 5. So there will be 5, 1, 2, 3, 4, 5. And again, they'll fill 1, 2, 3, 4, 5, and then they will start to pair up. Okay. The F subshell holds 14. You don't need to know this. You will not be expected at A level to do electron configurations involving the F orbital. The other thing, you are not expected to be able to draw the d orbital in any exam board for the UK. Okay, so how does this all come together? So we have the main shells. Those are numbered 1, 2, 3, 4, etc. And then we have subshells which we call S, P, D and F. As a general rule, the main shells will fill up in order 1, 2, 3, 4, and the subshells will fill S, P, then D. Okay? The first main shell can only hold S electrons, so it's only got an S subshell. The second main shell has an S subshell and a P subshell. The third main shell has S, P and D. Okay? The fourth main shell has S, P and D. We're not going to worry about any of the F orbitals because you're not going to be expected to do those at A level. So this is all we're going to worry about for now. Okay? So let's have a think. How can we do electron configurations for GCSE, for A level rather, using these examples? So we're going to look at the two examples we looked at before, which are carbon and sodium. I'm actually going to do carbon first because it's got fewer electrons. So carbon still has 6 electrons. So carbon still got 6 electrons, and the electrons are arranged in this order. So the first main shell has S electrons and there are 2, so it's 1s2. That's 2 electrons so far, we need to get up to 6. So the second main shell has 2 S electrons, we're up to 4, and then it's got P electrons, so we need to get up to 6, so that means we need 2 more, so it's 2p2. So it's 1s2, 2s2, 2p2, leaves us a grand total of 6 electrons. Sodium has got 11 electrons, so that is arranged 1s2, 2s2, 2p6, so we're up to 10 so far. The second main shell only holds S and P electrons, so now we go to the third main shell and it's the S subshell and it's 1. So that gives us 2 plus 2 plus 6 plus 1, which is 11. Okay, and that is the electron configuration for sodium, and this is the electron configuration for carbon. Okay, now you have a go. Try to write down the electronic structures of neon, chlorine and calcium. Have you done that? Good. So neon, 10. Okay, so neon is 1s2, 2s2, 2p6. Okay, and that's it because we've got 10 electrons now. Chlorine is down here, it's got 17 electrons, so its electron configuration is 1s2, 2s2, 2p6, 3s2, and then 3p5. Calcium, we're going to come and look at in a minute. So, annoyingly, it does get slightly more complicated when we get to 18 electrons, and the reason for this is because the 4s subshell is lower in energy than the 3d subshell, so it will fill first. So the electrons will go into the lowest energy subshells and the lowest energy main shells first. So because the 4s subshell is lower in energy than the 3d, it will fill before the 3d. So how does that affect things? So if we look at the calcium example we just had I asked you to look at earlier, it's got 20 electrons. So 20 electrons for calcium. So that means 1s2, 2s2, 2p6, 3s2, 3p6. So far so good. And then you might have gone on and thought, well, naturally the next one would be 3d2 because the third shell would be followed by the P shell is followed by the D shell. However, the 4s subshell fills before the 3d, so the electron configuration would be 4s2. Titanium with 22 electrons is going to fill, that should be titanium, is going to fill in a similar fashion, and that will be 1s2, 2s2, 2p6, 3s2, 3p6, not the 3d next, it's the 4s2, and then we need 2 more electrons to get us up to 22, which will be 3d2. Okay, so that is the electron configuration for titanium, and this is the electron configuration for calcium. Again, you can just double check that they add up to be correct. So 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 2 does equal 22. Okay, so there are some exceptions. It's chemistry, there's always going to be some exceptions. The exceptions to the general rules are chromium and copper. So chromium has got 24 electrons. So the electrons are arranged 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 is how you would think it would be, and that would be very sensible and that would make a lot of sense. However, there's something going on with the 4s and the 3d electrons. So the 4s subshell and the 3d subshell do something a little bit unusual. So if we were to draw out the electron configuration like this, we would see that the 2 electrons in the 4s subshell here are paired, and the 4 electrons in the 3d subshell are all unpaired like this. The electrons will always rearrange themselves to be more stable. So the 4s 2 electrons will rearrange themselves because it's more stable to have all the electrons here unpaired. So they'll actually rearrange themselves to look like this. So all of these 3d electrons are unpaired and this 4s electron is unpaired as it's more stable. The knock-on effect of that is this and this are no longer 4s2, 3d4. They're going to be 4s1. So let's rub that out. And let's rub that out. So it's not going to be 4s2, 3d4. It's going to be 4s1, 3d5. So 4s1, 3d5. That's not a very good 5, is it? Let's just write that out a bit more neatly. So the electron configuration for chromium is 4s1, 3d5. Copper is similar in the sense that it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s and 3d. So we've got, if it was 4s2, 3d9 is what it should be, but there's a similar situation going on here where it would look like this. So you'd have all of these electrons here would be paired except this one, and the 4s electrons would be paired, but they will rearrange themselves to be more stable. So it's more stable to have that 4s electron unpaired and all the 3d electrons paired. So the correct electron configuration for copper is 4s1, 3d10. It's more stable to have that subshell filled and that one unpaired. So that's copper and chromium. Those exceptions you would expect to repeat down, so for all of the elements in the same group as chromium and copper. So, abbreviated form. Abbreviated form is an easier way of writing out electron configurations rather than having to go through all the hassle of writing them all out. So, we represent in a square bracket helium, neon, argon. It's basically a noble gas, okay, or krypton. So they have the full electron configurations of all of these before. So for example, helium has got 2 electrons, which is 1s2. That's helium. So if I wanted to do, say, for example, beryllium, which has got 4 electrons, instead of writing out 1s2, 2s2, I can just write helium, because that's the 1s2 electrons, and then just do the electrons after that, which is 2s2. Okay, it's quicker and it's easier than having to write out 1s2. Perhaps you're thinking to yourself, why is that? It's not really the case for helium, because writing 1s2 is not that difficult. But when we get to something like neon, so neon's got 10 electrons, that'd be 1s2, 2s2, 2p6. That's the electron configuration for neon. So if I was to write the electron configuration for sodium, we've done sodium before, instead of writing out 1s2, 2s2, 2p6, we know there's 10 electrons there because neon's got 10 electrons. So we do neon, and then we can just fill the next subshell, which is going to be the 3s1. So sodium, in its abbreviated form, will just have neon 3s1. That's a lot quicker, it's a lot shorter than having to rewrite everything. Okay. And then finally, we could have a look at argon. So argon has got 18, which is 1s2, 2s2, 2p6, 3s2, 3p6. So instead of writing all of that out, you would only need to write out the ones that follow. So for example, calcium, you would write argon in square brackets. And then we don't need to write all of this out, we just need to go with the next subshell, which is the 4s subshell, so it's 4s2. Remember, the 4s fills before the 3d, so you don't have to write all of that out, that's the abbreviated form for calcium. Okay? So, blocks S, P, D and F. Okay, so the blocks in the periodic table tells us the outer subshell for that structure. So lithium, beryllium, the groups 1 and 2 belong to what we call the S block. We have the P block, which is over here. So this is the P block. So all the electrons in the P block will have an outer shell in the P subshell. This is the D block. All the electrons have an outer shell in the D subshell here. And this, which you don't need to worry about, but I'll tell you anyway, is the F block. Okay, so how can that be helpful when we're trying to do electron configurations quite quickly? Well, let's have a look at an example. Okay, so we'll stick with the examples we've already looked at. So for example, sodium, we know the electron configuration from sodium because we've done it loads of times. So we can work out very quickly the outer shell electron configuration for sodium. So the period in the periodic table are what goes across. So we've got the period 1 is the first main shell. So hydrogen and helium have the first main shell because they're in period 1. This is period 2, 3, 4, 5 and 6. Now I highly recommend you write the periods starting with helium. I always write them on the right hand side because it is very easy to mistake and forget that hydrogen and helium have a period by starting on this side. So I always say start on this side. So the electrons, it will tell us the subshell that they're in. With the exception of hydrogen and helium, they both have S electrons, okay, because it's 1s1, 1s2. But if we wanted to look at, say, carbon, now we know from before that carbon has the electron configuration 1s2, 2s2, 2p2. We can very quickly see that because carbon is in the second main shell, 2. It's the second element along in the P block, so the outer shell configuration is going to be 2p2 because these will all have p1, p2, p3, p4, P5 and P6. So you can very quickly see the outer shell electron configuration for carbon is 2p2. You can very quickly do the electron configuration because you can say, well, it's going to be helium in square brackets because of this bit that we talked about before. It's going to then have 2s2 because they're the second, this is the second shell, they're the electrons in the s orbital, s2, 2p2. You could quickly do something like sulfur. So sulfur's outer shell is going to be 3p, 1, 2, 3, 4. So the outer shell electron is going to be 3p4 for sulfur. So again, you could very quickly go, okay, so I'm going to track back to the next noble gas. I'm going to go, there's sulfur. I'm going to go all the way back to neon. Neon's got 10 electrons. So I'm going to put the electron configuration is going to be Ne in square brackets. And then it's going to be these electrons next, which is the 3s subshell, 3s2, and then it's going to be, it's the fourth one along, so it's going to be 3p4. Okay, so you've just saved yourself a bit of time. What I will say is when you come to do the D subshell, unfortunately this doesn't quite work because these are not the 4D electrons, these are 3D electrons. So these are 3D1, 3D2, 3D3, 3D4, etc. Okay, so that brings us to the end of the video. I hope that helped, and you can do electron configurations. So we've looked at completing the electron configurations. You only need to go up to 36, so hopefully we can tick that off. Hopefully you can write electron configurations in an abbreviated form, and hopefully you can identify the S, P, D and F blocks. What I would say is practice writing out all the electron configurations for all the elements in the periodic table. Once you can do that, check them off and make sure that you can do that in an exam. In the next session, we're going to be looking at ionization energies, trends in ionization energies, and the evidence for subshells and main shells existing. Thank you very much for listening. Adios.